I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
Space. Time.
the brain, life,
The universe.
Hello, this week, what exactly is a nebula? Can you cure yourself of diabetes? And are some groups of people better at driving than others? We are tackling the science questions that you have been sending in this week. My name's Chris Smith, and you're listening to The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
As we say, it's a Q&A show this week. You provide the questions, we provide the answers. And here to help me do that is our panel of guests. Helen Keyes is a psychologist. She's at Anglia Ruskin University. She's very interested in the psychology of driving, but also how the brain processes faces. Welcome to you, Helen.
Thank you very much.
I think it was Groucho Marx, wasn't it, the comedian from America, who said, "I never forget a face, but in your case, I'm going to make an exception."
Well, thank you. I appreciate that.
But not in your case. Very welcome to the programme. What do you do with faces then?
Well, I'm a bit of a narcissist, and I've spent a decade looking at why we think our own faces are special. So I look at self-face perception.
And what's the link to driving? Is that so you can remember the face of the person that you hit?
That's an excellent idea for my next study. But no, the link is visual perception. I'm really interested in how the brain processes things.
Thank you, Helen. Sitting next to Helen is Matt Bothwell. He's from the Institute of Astronomy in Cambridge. And what have you got sitting in front of you? You've got something there.
I do. I have a slightly strange thing called a stelloscope. If you imagine a black kaleidoscope with some date and time dials on the sides, what it is, when you look through it, instead of seeing a kaleidoscope, you see an image of the night sky. And it's a bit like a precursor to these apps you get on your phone nowadays that show you what's in the sky. It's a bit of an old school analog version of that.
Do you know where to look to see heavenly bodies?
Exactly. Or if you look in the sky and you want to know what's that, this will tell you.
I skipped over your show and tell, Helen, in my eagerness to talk to Matt. You got some goggles or something?
I've got some swimming goggles because I'm interested in the eye and the eye and brain connection. So I would like the listeners, if you're sitting beside somebody, to look at them sideways and have a look at their eyeball, because we assume the eyeball is like a sphere, but actually there's this quite gross lump right on the front, and that's your cornea. And your cornea is filled with some liquid called the aqueous humor, and that's the link with goggles. We remember from science refraction. When you put a stick in water, it looks bent. That's exactly what the aqueous humor does. The light is travelling through the air quite quickly. When it hits the aqueous humor, it bends towards the back of your eyeball. So this is why goggles work. If you're underwater, you'll know that you can't see very clearly. Everything is blurry. That's because no refraction is happening. So the light is travelling through the water. It hits essentially more water and doesn't refract or bend.
So it bends the wrong amount, which is why it looks blurry underwater.
Exactly. It's not directing light exactly towards your retina. So when we put our goggles on, it reintroduces this air liquid barrier, and so the light again will bend towards the back of your retina. So it's very clever. This is a nice first date conversation, I find, to,
Does it work?
Well, I only went on one date and I married him. It really worked.
It obviously does. Sitting next to Helen is Sam Virtue. He researches obesity and diabetes at Cambridge University. And Sam, you've got a packet of lard, appropriately enough, sitting on the table in front of you.
Yeah, I've brought in lard because what I actually work on in terms of research is fat tissue itself. And whilst lard may look just like a boring white substance, the tissue that it comes from is, in my opinion, the most fascinating of all tissues in the body. And adipose tissue, it secretes tens, if not hundreds, of molecules that can regulate all aspects of our biology. And it also has really important jobs of taking up fats after you're eating a meal and releasing them when you're asleep to keep you healthy. And we really think that this is one of the key things that goes wrong in obesity that then leads to diabetes.
And when you say it's releasing tens of thousands of molecules, are they like hormones and signals that will control how your body works?
Yeah, sorry, so tens to hundreds of different molecules, but it releases thousands of them. Yes, they're hormones that control how our body works. I mean, perhaps the best characterized one or the best known one is a molecule called leptin, which comes from the Greek, I think, leptos.
It means thin, doesn't it? Leptos.
Meaning thin.
So is that appropriate to say something that comes from fat is the word for thin?
Yes, because if you don't have this molecule, you will become spectacularly obese. And in fact, the people who they have found, humans with mutations in this molecule, would have actually died before the age of 5 if they hadn't had this leptin given back to them. It's very important for telling us about our long-term energy stores. For example, some female athletes will, and particularly distance athletes, will train so hard that their body fat percentage will drop extraordinarily low and they will stop menstruating. And that's because of a lack of leptin. And it's the way of the body saying you do not have enough nutrient reserves to have a successful pregnancy.
So it's a feedback loop that your fat knows how well fed you are, and it tells the rest of your body and your brain how well fed you are with these sorts of signals like leptin, and that then can regulate appetite and energy burn. Thanks, Sam. Well, sitting next to Sam is Peter Weathers. Now, Peter, you're very famous already. You do lots of these live, very explosive, exciting chemistry shows. So what have you got with you?
Well, I've got something that's potentially very explosive, but I'm hoping not to have an explosion today. What I'm holding is a test tube, but completely sealed, so both ends are sealed in glass. And this is because it contains the most reactive metal, and this is the element cesium. And this is one of my favourite elements. So it's actually so reactive that it would instantly react with the air or with any moisture on me if I broke the glass. I'm holding it very carefully. But it's actually stored under argon gas. But it's one of my favourite elements, and this is simply because it has a beautiful gold colour. So it looks just like gold.
It's beautiful.
And so now I'm just sort of holding it in my rather warm hand here. And I'm hoping that I should actually be able to get it to melt. So it's just beginning to melt now. So this is like liquid gold. It's absolutely beautiful.
Yes, it's running. It's running around like a liquid now inside the tube. So it's gone from a solid metal at one end of the tube, and now you're running it backwards and forwards, almost like mercury, which is another metal that's liquid at room temperature.
Exactly. So this is like mercury, except for it's got this beautiful gold colour. However, the gold colour, it turns out, is actually due to a trace impurity when oxygen has got in to react with this metal. So ultra pure cesium would be sort of silvery coloured, which is slightly disappointing because this gold colour is so beautiful. But it's actually just due to a tiny trace of oxygen there.
And if you were to drop that into some water, if
Like
I gave you my glass,
you've
you've got a glass of water there. Don't do it. But now I know what's in that tube. I know why you were so careful, because I asked you for a look at it and you said, please be careful. Now I know why. But what would happen if you put that in the water? Because people have seen the blob of sodium and the blob of potassium that's dropped into water at school. We do that quite routinely. What would happen with the cesium?
So this also explodes very violently. But unlike the sodium and the potassium, they are actually lighter than water. So they fizz around on the surface, which is lovely. Cesium is more dense. This sinks to the bottom, and this is, potentially very reactive indeed. In fact, it's actually the most reactive metal in the periodic table. Now, I'm sure there'll be some people screaming at the radio saying, oh, what about francium that's underneath cesium? But actually, there are some interesting features. You'd need to use relativity to understand why actually francium isn't quite as reactive as cesium. And so cesium is actually the most reactive metal that you could get. And that's why I think it's just absolutely beautiful.
Thank you very much, Peter. Now, let's just start off with some questions because, Matt, I've got this for you. Mikolek has got in touch on our forum. That's nakedscientist.com/forum. It's a great venue, by the way, to ask and answer science questions on any topic. What he has said is whether size matters. And he's specifically saying, would the size of a host planet determine the size of the life forms that might evolve and grow there?
So I really like this question. I think we should probably start with the caveat right at the beginning, which is that we only know of life on one planet, which is Earth. So as much as we're going to be trying to make educated guesses, they are still kind of hypothetical situations. That being said, the laws of physics do let us make a pretty educated guess, which is that size does matter, and that the direction it goes in is that bigger planets should have smaller animals. The reason for that is just because of gravity. So the bigger an animal is, the more massive it is, the more it has to fight against gravity to hold itself up. And so on a big planet with really strong gravity, a really massive animal is going to be doing really, really badly. You can see an example right here on planet Earth. The biggest land animals that ever existed were dinosaurs. But in the ocean, where the buoyancy of the water slightly counteracts the force of gravity, it kind of simulates a low-gravity environment almost. And so ocean creatures like whales can be much, much bigger than any land creatures. So we would definitely expect that big planets would have small animals and vice versa.
There's also another possible effect to superimpose on this, isn't there? Which is you get this phenomenon here on Earth called island dwarfism. Not Ireland as in where Helen comes from, as in Ireland, a thing surrounded by ocean, which is where you have a small landmass, where the resources are limited. You tend to have smaller animals that are better able at not exhausting those resources than say, a big animal which would munch its way through all the vegetation very, very quickly. And so in the same way that we think certain other animals have shrunk over evolutionary time when they've been dwarfed in that way, there's evidence that humans or human ancestors, this has happened with the island of Flores, where the Homo floresiensis, these hobbit people, actually were thought to have evolved in a limited area, and therefore they may have been forced to become small.
That's really interesting. I guess on a planetary scale, a planet would have to be very, very small indeed for that kind of effect to kick in. So I think a complete lack of gravity might be a problem before limited resources.
Thank you, Matt. Helen, one for you from Katie goes as follows.
Are motorcyclists more risk-prone than car drivers?
So what do you think? Motorcyclists versus car drivers, are they more hooked on the adrenaline? Are they more prone to be risky?
There's a bit of a misperception here. So motorcyclists are certainly more vulnerable road users than drivers. In fact, motorcyclists are 10 times more likely to be involved in a fatal accident than car passengers are. But it's not necessarily motorcyclists that are at fault here. So there's two reasons that drivers tend to hit motorcycles, and they're to do with what we call look but fail to see errors. So this is when a driver looks up the road, a motorcyclist is coming and they see it, but they fail to notice it or take the motorcyclist into account. There's two reasons this happens. One is just straightforward visual perception. We just call it conspicuity, how conspicuous the motorcyclist is. And it just doesn't stand out against its background in the same way a car does. There's been a really nice solution to this problem, which is the inclusion of daylight running lights on motorcycles, or DRLs, which are lights that are always on during the day. And we know that this can increase their visibility by up to 40%. So this is fantastic. But I'm much more interested in the other type of error, the other look but fail to see error, which is cognitive conspicuity error, which is when drivers see the motorcyclist but almost don't register the motorcyclist. This only happens with experienced drivers. So an experienced driver is much more likely to fail to spot a motorcyclist than a novice. And that's quite interesting.
That sounds paradoxical, doesn't it?
It does. And it's because our brains are so good at using heuristics or relying on patterns that have worked before. And it's not really lazy, it's economical. So the brain is a very clever thing. And experienced drivers are used to looking up the road, seeing other cars, taking them into account. So it's almost like we almost cognitively sometimes don't see the motorcycle or the cyclist or pedestrian because we're not expecting to. So it would be quite good if we could maybe increase cognitive awareness of motorcycles, not just visual perception.
Sam?
On that, does this make cyclists safer in Cambridge than in an equivalent sized city? Because there are so many of them relative to another city that motorists are actually more aware that they're likely to be there.
It absolutely should. So if we're going by the cognitive conspicuity theory, it absolutely should make them more visible cognitively to drivers, yes.
And if we go by the death rate and accident rate and everything else, does it bear up?
It does, absolutely. Our statistics are better than other parts of the country.
That's a relief. Thanks for that. Now, Sam, we've got this question which we'd like you to break down and digest for us. It comes from Don.
Why do our bodies get tired or we feel like sleeping after an overly large meal?
Now, we've all been there, had as the Americans like to put it, the effect you get with too much turkey at Thanksgiving. Why does this happen? Can you help Don out?
Okay, so basically what happens when you eat a large meal is that you take on board a lot of nutrients, and some of the nutrients directly, but also indirectly by causing the production of hormones from the guts, can signal to the brain. And for reasons which are slightly hard to understand how they evolved, sleep and eating are very closely related. When you've eaten a large meal, it activates sets of neurons in the brain, which are also associated with sleep. And you kind of think about this, if you've just eaten a large meal and you're out in the wild, well, you're already pretty fat and slow from all this food, and now you're going to fall asleep? That might possibly make you a really easy prey. But perhaps a more positive way is to think maybe you crawl off to a nice hole because you don't need to go looking for food.
Assuming you can still fit into it.
Assuming you can still fit into it.
Like Winnie the Pooh got stuck, didn't he? Too much honey.
Oh, yes, yeah. So I have small children, so I've been reading that quite recently, yeah. So anyhow, the neurons that everything seems to converge on in the brain are called orexin neurons. And it's quite interesting because these were found in by two different groups of researchers at the same time. One group found them in mice, and they called them orexin neurons because the mice were fat. So they assumed that this was something involved in eating. However, the other group that found them in dogs. And the much more striking feature of these dogs was the dogs would bound along and then have a narcoleptic fit and just pass out and roll over, and then suddenly just get back up as though nothing had happened. And so they thought these were to do with sleep, and it turns out it's both.
Were they Labradors, these dogs? Because in my experience, Labradors just eat anything until they pass out. And then they sort of sleep it off and then come back to life and do the same again, rinse and repeat until they've gained about 30 stone.
Yeah, I think they're Doberman Pinschers, the dogs with narcolepsy. But yeah, it's really amazing if you see a video of a narcoleptic dog, because they will be in like the middle of a game of catch and then just fall over and sleep. So yeah, things from your gut like glucose and insulin after a meal signal these and they make you feel sleepy.
And the purpose of doing that is you need to divert a lot of resources to processing that enormous meal and then absorbing the calories and distributing it around the body, I presume.
Yeah, so that's certainly one theory as why this has evolved. So, for example, a snake increases its metabolic rate 5-fold after ingesting something like a piglet or something, and that's all
big
the
snake,
energy.
A piglet, a big
Python,
snake,
something like that. But or whatever it's eating, a mouse or whatever. So yeah.
But the interesting thing about a snake is that might dine once a month, once every several months, whereas we have to eat regularly. Is that just a reflection on the fact that a snake is cold-blooded, has a lower metabolic rate and can literally sit there not burning off much energy, so it doesn't need to eat, whereas you and me are ferociously burning off calories, so we need to replace them?
So yeah, I mean, there's certainly an element of that. But it is kind of interesting when you think how long humans can survive without eating, because we can go many, many days, if not months, without eating. So why we have evolved these patterns of eating more regularly versus other animals which do not eat very regularly. I mean, there are mammals that don't eat for months at all, like a bear, when it hibernates, doesn't eat. So why we have these specific patterns is quite an interesting question. I'm not really sure I have a good answer for it. Someone might.
Thank you very much, Sam. You can call that food for thought, perhaps.
Got a biological brainbuster or a chemical query? Ask the Naked Scientists.
I just wanted to know about sleep paralysis. Is it a disorder or condition, and can it be cured?
How much energy is in moonlight? And could solar panel technology be used to capture this energy?
When you cook food with any alcohol, how much, if any, percentage of the alcohol stays behind?
Every Friday, the Naked Scientist and Cape Talk unravel the science behind those weird and wonderful questions you've always wanted to ask. Download and listen for free at thenakedscientist.com/ask, or simply search and subscribe to Ask the Naked Scientist on your favourite podcast app.
This week on The Naked Scientists, we're putting your science questions to our terrific team, who are astrophysicist Matt Bothwell, chemist Peter Wuthers, psychologist Helen Keyes, and human physiologist Sam Virtue. If you'd like to get in touch or send in a question, it's chris@thenakedscientist.com. You can also find us on Twitter @Naked Scientists. Georgia Mills has tweeted, she's one of our producers, she said, "What could go wrong? Peter Wuthers has brought in a tube of cesium to the Naked Scientist studio," and there's a very nice picture of Peter with his cesium there. Now let's jump right in with a question for you, Peter. Garth sent this into our forum, actually. He says, what's ozone? I've heard it's bad for the environment, but does it have any beneficial effects?
So ozone is a form of oxygen. Now, of course, we breathe in oxygen every day, all the time, to stay alive. But the gas that we're breathing in is composed of 2 oxygen atoms united. So this is an oxygen molecule with the formula O2. Ozone is a different form of oxygen, where actually 3 of these atoms of oxygen are united together. And this has completely different properties. This is poisonous, and it's poisonous because it's too reactive for us. So ozone can be used as a disinfectant, for instance. It is incredibly reactive. In the same way that bleach is very reactive, it can destroy tissue and so on. And this is the sort of action that ozone will have on our bodies if we breathe this in or are exposed to it in high concentrations. But it can be useful. Of course, I mean, everyone's heard about the ozone layer, and that's a slightly different thing. This is actually partly used to protect our environment from ultraviolet light that would otherwise be hitting the Earth. But ozone itself in low concentrations can be used. So, for instance, I was walking into a toilet the other day. There was this very strange smell of, and I thought this must be ozone. I thought, am I going mad here, or is this really ozone that I can smell? And I mentioned,
well, it was a toilet, Peter.
Well, it was a toilet, yes. But and eventually, I looked around and found, at long last, this ozonizer that had been stuck on the wall. And there are now companies that are making these things because it's actually a very easy form of disinfectant, because you can produce ozone in small concentrations simply by passing an electrical discharge through oxygen.
So a spark?
A spark, yes, exactly.
And what does that do to make the ozone then?
So the energy from this spark will rip apart O2 molecules, and then you will, for a short period of time, get these incredibly reactive oxygen atoms. Now, they don't want to stay like that, which is why we would, of course, be normally breathing in O2, where two of them have bonded together. And maybe if these two oxygen atoms find each other, they will reform an O2 molecule. But of course, it's far more likely that one little oxygen atom will bump into another oxygen molecule rather than the other part that just fell apart, the half of this. And so that would then form an O3 molecule. And so actually this is why you could, anywhere that there's a spark, regular sparks, you can sometimes smell this sort of slightly peculiar smell.
When
so
you use
for
power
instance,
tools, for example, a drill or a hand blender,
or
hairdryer.
Dodgem cars.
Yes, you get that very distinctive smell, and that's ozone, is it?
Is
it just ozone?
No, it could also be. So when you spark through air, of course, air that we breathe in is not just O2 molecules.
There's a lot of nitrogen in there,
exactly.
Isn't there?
So the main gas is nitrogen. And so the other thing that you can easily form are oxides of nitrogen. And so those also have a rather peculiar smell. So sometimes it's not quite clear whether we're smelling the ozone or the nitrogen oxides.
And just returning to your former example, did the ozonizer in the toilet help to neutralise nasty nifs or not?
I'm not sure whether it's for nasty nifs or for any potential pathogens to some degree, if they're sort of just on the surfaces. But it certainly smelled better than usual.
Terrific stuff. Thank you for solving that one for us, Peter. Right, Matt, Lloyd wants to know, why do stars group into galaxies with enormous distances between them? Why does the universe look the way it does, I guess is what he's saying.
That is a really big question. Why does the universe look the way it does? It's also a really good question. Why do stars form these structures we call galaxies rather than just being like a uniform sea of stars filling the universe? The very, very short answer is because gravity made it that way. If we go back to the very, very early universe, so before stars and before galaxies formed, the universe actually was very, very uniform. But it wasn't completely uniform. There were little differences in the distribution of matter just because of random chance. So, this little bit of the universe over here might have a bit more matter than average, and this bit of the universe over there might have a bit less matter than average. And the action of gravity kind of magnifies or amplifies those differences. So the bit of the universe that has a bit more matter than average will have a bit of a stronger gravitational pull because of all of the matter, and so it will kind of gobble up more matter than the less dense regions. And so there's a bit of a runaway positive feedback thing where the more dense regions grow and grow and grow, and all the other regions get emptier and emptier and emptier. So eventually you fast forward and the universe ends up looking quite blobby with these very, very dense regions, which eventually turn into galaxies, separated by big empty spaces.
And that's where we are today.
Exactly, yes, that's where we are today. So these blobby regions eventually, once stars start forming, these blobby regions eventually turn into galaxies, which is why the universe looks the way it does.
Now, that's a pretty basic question. So let's ask you something a little bit harder then. So what's the ultimate fate of the universe then? Because it is growing all the time, isn't it? It's getting bigger. As far as we know, the older it gets, the faster it's growing as well. So what's the ultimate fate? Does it just get bigger and bigger and bigger ad infinitum?
That's a very good question that I don't think we totally know the answer to. It all depends on what dark energy is doing. And we don't know very much about dark energy at all. It was only discovered in the late 1990s. So we've known for about 100 years now that the universe is getting bigger and bigger and bigger. The universe is expanding after the Big Bang. But when astronomers in the late 90s went to measure the rate of this expansion, it actually turns out, against all expectations, that the expansion is getting faster and faster and faster, that there's some mysterious stuff in the universe that seems to be pushing it apart at the seams. We've called this dark energy. That's the name for the effect. We don't really understand what it is. And so it could be that in the very far distant future, dark energy gets stronger and stronger and stronger and eventually just tears the universe apart at the seams. But like I say, we've only known about this effect for about 20 years, and I think we have a lot more to learn before we can say any real answer.
So if the universe is inflating in this way, does this mean then that given enough time, when you get your stelloscope out, it could just be a very boring thing that you see, because everything could have got so far away and is moving apart from us so fast that it's going faster than light can travel to us, so you just see black space?
That could be true. So there's this concept in cosmology called the cosmic horizon. So very much like we have a horizon on Earth, it's parts of the Earth that we can't see because the surface kind of curves away from us. There are regions of the universe that we completely can't see because the light hasn't had time to reach us. So any light that needs more than the current age of the universe to reach us, the light hasn't had a chance to reach us, so we can't see it. And as the universe kind of accelerates and dark energy gets stronger and stronger, the cosmic horizon is going to actually get closer and closer to us. More things are going to fall over the cosmic horizon. So as time goes by, we're actually going to be able to see less and less of the universe.
That's a sobering thought, isn't it?
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
It's Q&A week this week on The Naked Scientists, and we're answering the science questions you've been sending in with the help of our very brainy panel, who are astrophysicist Matt Bothwell, chemist Peter Wuthers, psychologist Helen Keyes, and human physiologist Sam Virtue. Still to come is the stuff that comes out of my tap, 100% water. One of you is wondering also, why do women tend to live a bit longer than men? And is it safe to listen to the radio while driving? Well, that one we're going to tackle right now, because that's come in from Izzy. For you, Helen.
Hi guys, I drive into work at the Naked Scientist office, so I was wondering, is listening to the radio whilst driving actually safe? And how does it compare to using a mobile phone? And is hands-free okay?
Go on then, Helen. Should we be telling all our listeners who are tuned to this programme, hooked on your every word, and they're driving, to turn us off? Please say no.
Fortunately not, we're lucky. So there is one instance in which listening to the radio can be very dangerous for driving, and listening to speech is fine. In fact, in some ways it can keep us awake and stimulate us, so it can have preventative factors. But there's a caveat to that, so we shouldn't listen to things that are heavily visual. So when we are listening, for example, to sports matches on the radio, this is a really bad idea. So simply because we're recruiting the same parts of our brain. So when you're using your visual imagination to visualise what the commentator is talking about, it takes our visual attention directly from the road, and we know that this is really hazardous.
It's not just when people fling their hands up and go, yes!
Yeah.
And they take their hands off the wheel. It's not that.
Not quite that dramatic, but just any sort of visualization task is a really bad idea when we're driving. And the second part of that question was about how does it compare to mobile phone use? Mobile phone use is quite interesting, and we like to usually compare it to having a conversation with a passenger. So mobile phone use is a lot more dangerous than having a conversation with a passenger. And indeed, you're about 4 times more likely to be involved in a crash if you're on a mobile phone compared to speaking with a passenger. And we know that there's no difference if you're using a hands-free set. So I think that would surprise some people. So it's not necessarily about looking at your phone or using your phone. It's about the speech. Producing speech and listening to speech is quite complex. It seems easy to us because it's so effortless. That's merely because the brain devotes so many resources to speech perception. But actually, when we're talking on a mobile phone, we know that there's a higher instance of questions being asked and answered, and there's a higher number of utterances per minute when we're on the mobile versus talking to a passenger. So that makes it more dangerous. It takes up more of our resources. But secondly, it's really interesting. If you're speaking with a passenger in your car, they will moderate their conversation to the road environment. So if you're a driver and you're approaching a roundabout and your passenger is speaking with you, they will automatically stop speaking, or they may even talk about the traffic, say, oh, look, here's a traffic jam.
Or if they're my wife, they flinch when they see something coming.
Flinching is very helpful.
And it is actually, because it gets your attention, doesn't it? And it makes
does.
you think, oh, and then you realise, yes, you are getting a bit close to that.
It does. So obviously, if your wife is on the other end of the phone, she may be just asking you a question, and she wouldn't be moderating her conversational behaviour. So do not speak on a mobile phone, including hands-free. And we are really trying to push to get hands-free to be made as illegal as using your phone in cars, because there's no difference there.
Thank you very much. Peter, can you very quickly for us answer Kit's question, which is the water that comes out of the tap actually 100% H2O? If not, what else is in there and why?
If it were 100% H2O, my job would be a lot easier in many ways, because when you're carrying out chemistry experiments, you need to try and control all the variables, things that could change and you don't know quite how they're changing. And one of the things, of course, is anything that might be in your solvent, which could well be water. And we go to great lengths to try to make pure water, and this is incredibly difficult. So the purest sort of water that you can commonly come across would be distilled water. And this is where you are heating it up and then turning it into steam and then condensing this. But what you're trying to remove here is what would be naturally occurring, certainly in any bottled mineral water that you buy, and also wouldn't really be removed unless there were extreme levels from any tap water. And these would be certain dissolved ions, such as sodium ions, potassium ions, magnesium, calcium, all of these things.
Calcium, as I well know where I live.
Exactly. So these are the things that would naturally be in water, and they're not really worth removing from tap water. So they're definitely present there, and it's very difficult to remove some of these things and not worth the effort generally. But of course, some other things are added, and perhaps one of the most controversial things is fluoride ions. There's absolutely no doubt that this has helped tackle tooth decay in this country because it protects the teeth, makes them much harder and more resistant to decay. So that is something that is deliberately added in very, very small concentrations and highly monitored, but this can be very good for us. So it's definitely not pure 100% water.
Thank you very much, Peter. Right, everybody, you've been answering the questions that everyone else has sent in. Now I've got a little quiz for you. So we're going to divide you up into two teams. We're going to have team 1, that's going to be Matt and Helen, and team 2 is going to be Peter and Sam. You can confer within your teams for each question, and if you get it right, you get a bing. If you get it wrong, you get a bong. And it's going to be the person with the most points who are going to be the winners. And I hope I add the scores up correctly, because it has been known that sometimes I've robbed people of their victory by not paying attention well enough. So here we go. First question. This round is called Food and Drink. We've talked a lot about food this week and drink. So appropriately enough, here's your question 1. What is the chemical with the molecular formula C2H6O, better known as?
Is that caffeine?
You seem very confident, so yes.
That's just me.
Caffeine. No, I'm really sorry. I know Peter's waving his hand around. What do you think it is?
Well, presumably this is going to be ethanol, isn't it?
It's alcohol. Yeah, very good. Okay. Okay, over to team 2. This is Peter and Sam. If you took some 1,3,7-trimethylpurine 2,6-dione into your body, what would you be consuming?
Could you say the name again, please?
1,3,7-trimethylpurine 2,6-dione.
This probably is going to be caffeine or...
Go for it.
Yeah, let's go for that.
You're right. It is actually.
Thank you.
It is caffeine. So that's 1 to team 2 so far. And
don't we get the bonus?
No, you're just showing off. Right, okay, here we go. Back to round 2. This is called Count Those Calories. Okay, over to Matt and Helen. What has got more fat in it, a coconut or a Big Mac?
I would guess a coconut.
I would guess coconut as well.
Any suggestion on by how much for a bonus? 200%
more.
Okay.
Do I sound confident again?
The answer is indeed the coconut. It's a prodigious amount of fat in a coconut, actually. There's 33 grams per 100 grams fat in a coconut. It's all saturated fat, so it's not terribly good for you. A Big Mac's 15 grams per 100, so it's actually got twice as much saturated fat per weight as a Big Mac. So that's a point for you. So you're off the bottom and so far level pegging. Let's see if they're going to maintain their lead. Team 2, what contains more calories, boiled egg or bowl of porridge?
More calories? It must be a bowl of porridge.
As in, like, one boiled egg versus a bowl of porridge?
Yeah.
And is the porridge made with water or milk?
I think
a bowl of porridge that you'd get in Scotland.
Oh. But I mean, actually, so what was the mass of the dried porridge versus the mass of the egg? I mean, I think that's what it's got to come down to.
I'd
go for the porridge, surely.
Going porridge?
Well, I don't, you're the expert here on food, aren't you?
Yeah, well...
That's called covering your backside, I think.
Yeah, so I think I'm going to be bold and say the egg.
You're going egg?
Sorry, Peter.
No, you should have gone with your gut, because it's the porridge, 170 calories versus 150 for the egg. If you'd said, I'm going to go egg and have soldiers, you'd have been right, because a buttered piece of toast is 75 calories, and then the egg would have won. But it was a close thing. Okay, so it's still level pegging. So there's everything to play for. Back to team 1. Matt and Helen, here we go. Now, listen carefully to this. I'm going to say this in the eponymous words of LOLO, only once. Are you ready? Beverly buys a melon and an orange for £1 10p. The melon costs £1 more than the orange. How much was the orange?
Like 5p, right?
Yeah, 5p. £1, 5p.
Yeah.
I don't know why I'm putting my hand on my mouth like a secret. £1 and 5p and 5p. It has to be, yeah.
You've got a psychologist on your team, you see, so they don't fall for tricks.
I also
like
lecture
that.
in statistics.
Yes, it's a trick.
So I had to get that one right.
Everyone, when they hear it, immediately subtracts one thing, the other goes 10 pence.
Yeah.
And actually, it's not. It is indeed
not
5p.
us, though.
And we will publish the answer on the Naked Scientist website, actually worked out with algebra to prove to you, if you don't believe us, the orange is 5 pence. Right, so that's a point for Team 1. So that's 2 points to Team 1 so far and 1 point to Team 2. So to stay in the game, Team 2, you've got to get this one right. listen very carefully. I shall say this only once. 2 fathers and 2 sons sit down to breakfast together. They eat 3 eggs exactly. Exactly. Everyone has an egg. How?
2 fathers and 3 sons.
2 fathers and 2 sons.
2 fathers and 2 sons.
Sit down for breakfast. Is it possible one of them has an egg and doesn't eat it? It's a nonsense answer. I don't have.
Is that your answer?
No.
Whether a grandfather or something or whatever.
Yes.
Yes, grandfather and son and his son.
I don't believe it. Got away with it. Yes, that's absolutely right. One of the fathers is a grandfather, so therefore the other father is both a son and a father. There are 3 people at the table. You just assume, first of all, that there are 4. Trick question. OK, it's a tie, which means it goes to our tiebreaker. This is a Guinness Book of Records tiebreaker. Everyone's involved, so the nearest answer is going to win. So what I'm going to do is ask you to confer, and then you will produce an answer each, and the person with the closest answer is going to get the prize beyond price, which is the Naked Scientist's Big Brain of the Week. OK, according to the Guinness Book of Records, Otto the English Bulldog has skateboarded, that means pushed once and then sat on the skateboard through the longest human-made tunnel. That's as in skateboarding between people's legs. How many people were in the record-setting line that Otto, the English Bulldog, skateboarded through? Confer now. You've got a couple of seconds.
Is this pushing continuously or one push?
No, it says it, as I clearly read, Pete, you just weren't listening properly. It says pushed once, then sat on the skateboard.
And was he or she on a hill?
Doesn't matter. It's irrelevant.
Yeah, exactly. You're going to crash into the side, isn't he?
But it is a Guinness Book of Records. It's a
yeah, but how many people are going to be doing that?
Okay, going to hurry you?
All right.
Okay, so we'll come to Team 1 first. Say a number of humans in a row.
20.
20,
You're going to go 20. What do you think? Team 2.
Well,
25, not...
Yeah, we had 25 as well.
Yeah, we said 25.
The answer is 30.
Oh.
Otto likes hanging out with his best mate and fellow bulldog Lola, who apparently also is fond of skateboarding. So, Team 2, you have clinched victory from the jaws of defeat, and you are this week's Naked Scientist Big Brains. Give yourselves a big round of applause. I said a big round of applause. That was a very half-hearted round of applause. Now let's jump right in with a question for you, Sam. You're a human physiologist, because Sam has got in touch and would like you to help out with this one.
Can you cure yourself of diabetes?
So can you cure your own diabetes?
Well, the short answer is some people can, and it's probably worth giving it a go. A lot of this research came from patients who were going to be undergoing bariatric surgery. And one of the things they aim to do before people have the surgery, because it's quite hard to do surgery with lots and lots of fat around, is try and get them to lose some weight. So they put them on very low-calorie diets for several weeks ahead of the surgery. And they actually find these were pretty beneficial. Researchers led by a guy called Roy Taylor up in Newcastle have really been looking into this a lot. And they basically put people on a diet which is about 600 calories for 8 weeks, and we normally eat about 2,000 calories, so that's a third of what we would normally eat. So this is pretty extreme. And when they looked at these subjects, they lost about 14 kilos over the 8 weeks, and about 40% of them had recovered from having diabetes. And it wasn't just that they were more insulin sensitive, their pancreas could make insulin again.
Should we point out that we're talking about type 2 diabetes rather than type 1 diabetes, where people are absolutely dependent on insulin to stay alive? Type 2 diabetes is the obesity-associated diabetes that you would be working on.
Absolutely. And one of the things they found about the subjects who could basically reverse their diabetes is before they started the weight loss, these were the subjects who already had reasonable amounts of insulin. So if people had had diabetes for a long time, over 10 years, or they have very, very low levels of insulin, it was likely their pancreas was so badly damaged, just like a type 1 diabetic, where the beta cells are destroyed by the immune system, that they couldn't recover. But subjects who had high blood glucose but high insulin, they just weren't making enough insulin for their body, they were the ones who were most likely to recover.
Do we know why, when a person does carry a bit too much weight, that the body's tissues essentially become deaf to their own insulin signals? So they can have, paradoxically, very high insulin levels but very high sugar levels. Do we understand that process?
That's exactly what I work on, and there are several theories about it, but the one we're interested in is the idea that fat can accumulate in organs where it shouldn't. So fat can accumulate in liver, and the fat itself is what then poisons the cells and interferes with the signaling, essentially muffles the ability of the insulin to pass its signals down to do the things like, say, take up glucose.
And so when one loses weight to a profound degree, you rob away some of that abnormally accumulated fat, and therefore that muffled signal, the muffler is removed, and now you can again see the insulin signal.
Indeed, and also fat can actually interfere with the production of insulin by the pancreas. And one of the things they saw in the study was in the subjects who particularly recovered well, they had much greater reductions in lipid within their pancreas. So yes, that's very reasonable.
Thank you very much, Sam. Peter, one for you. D says,
we say that acids burn, but they're not necessarily hot. So how is this different to something like boiling water?
And I just want to link on because we also heard from Jake on a similar theme who says, what naturally occurring substances also have the most extreme pHs? If you could sort of tack that one on too, please, Peter.
Yes, so of course the burn that we're talking about here is actually just damage to the tissue, and that's the thing. And that's actually, of course, that our tissue can be relatively easily damaged. An easy way to do this is to pick up something hot, and that's going to damage the tissue there. But actually you can get burns from, of course, cold things. And so we were talking earlier about liquid air being extremely cold. If you were to certainly dip your finger into liquid air, and I do not recommend this for any period of time, you would destroy all the tissue there. But a small splash on you may well cause a burn as well. But of course, yes, you can indeed also get burnt by acids. And again, this is just causing damage to the tissue. We normally have mechanisms to control very precisely the pH of the fluids in our tissue and so on. And adding concentrated acid is absolutely very far away from these normal conditions, which is why the damage is going to take place. But this is rather interesting. So tagging this on to the other question about the extremes of pH, actually it is possible to find incredibly acidic solutions in nature. And this is in certain mines, notably ones that have pyrites. So this is iron sulfide, a form of iron sulfide with the chemical formula FeS2. And this reacts with oxygen and water and can produce incredibly strong, powerful solutions of sulfuric acid. And then to tie these two together, actually, there's a beautiful story from the Middle Ages in various books on stones and so on. It's called the fire stone, which probably is actually because you can use it to start fires by smashing it into a flint. But actually, there are also descriptions that if you squeeze this tight in your hand, it will burn it. Now, of course, maybe you're thinking that it's going to be burning in terms of because it's really hot and fiery, but actually it could burn your hands because the surface of this, again, if there's moisture there and has reacted with the oxygen, could produce acid. And so actually you could get an acid burn from this mineral by holding it very tight. So actually these acids do occur in nature and they can be incredibly strong. In fact, some of the record pHs are at -3. Now, this sounds very odd, but strong sort of laboratory sulfuric acid, you'd get sort of 1 molar, and this would have a pH of, what's this going to be, of 0, is it? Yes,
0.
That would be 0, yes,
Yeah.
good. And so less dilute is actually a pH of 1, but so this is really concentrated when it starts going to negative, and so really very strong solutions of sulfuric acid.
Matt?
Is there a theoretical endpoint for the pH scale? Can you just keep on making stronger and stronger acids forever? Is it just like a practical limit, or is there a theoretical limit to how strong an acid can be?
That's
because I was nasty to him about the universe. He's getting his own back now.
Oh, this is quite a good question. So, of course, I mean, the pH scale means it's the concentration of hydrogen ions per volume. And so we are limited here. So in the same way that actually there's a concentration of pure water, how much water you'd fit in a certain volume, unless you start compressing it in a neutron star or something, there's a limit to this. So pure concentrated sulfuric acid would be sort of a limit in some sense. But then what's really makes an acid is the water that's also present. So it's a little bit difficult. So absolutely, there is definitely a limit. And you can't put too many protons in a solution of water. And it's the protons that are making this thing acidic.
Thank you very much, Peter. Now, I'm glad you stuck your head above the parapet there, Matt, because I've got this question from Francesca for you.
What is a nebula? How do they form? And why do they look so different?
So a nebula is just the name we give for a cloud of gas and dust in space. The name nebula comes from the Latin, meaning clouds. There are all different kinds of nebula, and the reason they look so different is for the same reason that clouds on Earth look different, just because there are different types and they form in different ways. There is a type called a H2 region, So a H2 region is a star-forming cloud in space. So it's like a big cloud of molecular gas that is collapsing under gravity and turning into stars, and it gets illuminated by the light from the young stars and glows very nicely. So the Orion Nebula is a nice example of this. There are other nebulae called planetary nebula. These are actually completely different formation mechanisms. So planetary nebula are clouds of gas that are blown out by stars, like towards the end of their life. The name's a bit of a misnomer. They were, when early astronomers saw them, because they tend to be round, they thought they resembled planets, so they called them planetary nebula, but they're caused by dying stars. Galaxies as well. Before we understood what galaxies actually were, they were called spiral nebula. So about 100 years ago, astronomers incorrectly thought that galaxies were kind of whirly clouds inside of our own Milky Way, but now we, of course, understand that they are, much, much further away than that.
Thank you very much for that one, Matt. Right, well, you and Peter might like to come in on this one between the two of you, because Steve Rampley has emailed chris@thenakedscientist.com and says there are no perpetual motion machines. His words, not mine. But what is the most efficient machine known? Do you agree, that the pair of you, that there are no perpetual motion machines?
So,
is that true?
So perhaps part of what people were trying to do when they were trying to create perpetual motion machines would make something that would always be moving. And that is something that, of course, does happen in that, for instance, vibrating bonds. So a simple, going back to our oxygen molecule, O2, this molecule is always vibrating. So it is always moving. In fact, even if you cool this thing down, even to absolute zero, it is still going to be moving, which is quite remarkable.
Really? I thought at absolute zero it did stop. Is that true?
I think it has to be moving, yes.
Really? Is that the case?
Wow.
So there is. So nature has already invented a perpetual motion machine.
But the problem
is
you can't get it to do anything useful. And so if that's what you want out of your machine, so this comes back to the efficiency thing, then there's a problem.
Okay, so Peter has challenged Steve's contention that there are no perpetual motion machines. What do you think, Matt, about the idea about efficiency? What does he actually mean by efficiency, though? Matt, what is that?
So the efficiency of a machine is just the amount of useful work you can get out of the machine divided by how much energy you put in.
And so what sorts of levels of efficiency might we consider for various things around us, in the world around us, then?
Well, the question actually is, why is some of this energy lost? And so why can you not convert all of your energy into useful work? And then this comes down to the idea of disorder and entropy, that this is the key driving force, in a sense that everything is getting more and more disordered. And some of this energy, in a sense, is actually creating a lot of disorder. And this is what every machine has to do, that there's, you can't convert all of your fire heat energy into lifting a weight, for instance. Something is always going to be lost.
Indeed, a coal-fired power station's 50% efficient, isn't it? Between 30 and 50%. A car is about 30% efficient. So in other words, 70% of the fuel that you burn does not turn into movement of your car, which seems ridiculous, doesn't it, when we put it in those terms?
It sounds pretty ridiculous. I think some of the more efficient engines would then be working on fuel cells, which is a very efficient way to get that energy out of the chemical energy there.
And this is where you're exploiting the energy in bonds between components, isn't it, to actually make bonds in order to release some energy?
Yep. But even so, I mean, it is absolutely impossible to convert 100% of your energy into useful work energy. So you're never going to get to 100%.
So it's worth going to the gym, because that's kind of useful for where you come from, isn't it, Sam? With the obesity business, it's a damn good job that the body isn't 100% efficient, because it would be a lot harder to get that weight off down the gym.
I mean, also, biological systems are essentially machines as well, and they're pretty good. I mean, the efficiency of us as humans when we're running will be over 30%, and that's fairly equivalent to some of the better motor cars. So, yeah. And what humans really turn their energy into is heat. So that's what we mostly lose it as. So if we go to lift a weight or something down at the gym, maybe about 30% of the food we'd be consuming is going into lifting it, and the rest is going into heat production.
It's kind of good, though, because when you're chilly and you shiver, you're basically making your muscles do lots of pointless work and releasing lots of heat as a byproduct, which you then shove back into your body to warm up on a cold day.
Yeah, absolutely. And actually there's another type of organ we work on, which is called brown adipose tissue. And this is an organ where its express purpose is not to store energy, but to convert energy into heat. And so small organisms like mice, rats, and in fact infant humans have a lot of brown fat. We now know some adult humans have brown fat. And so I wonder if I could cheat and argue that this is a very, very highly efficient organ, because all it does is convert chemical energy into heat, and that's its purpose. And so, in a sense, its very inefficiency, by the classic sort of definition of how much work do you get out of it, makes it incredibly efficient at doing it.
Because, as you say, kiddies have a lot more as a proportion than adults. We lose it as we get older, don't we? Is that because children just have a very big surface area to volume ratio, so their rate of heat loss can be much higher, so they have a bigger challenge staying warm, so they compensate by having this brown fat? Or is there some other reason why we lose it? Does it burn itself out as we get older?
No, it's essentially what you've just suggested at the first point. It's a device for making heat. Many adult humans, and a good proportion of them, do have brown fat, but it's certainly more prevalent and more active in infants. And so, being a bit of a geek, I have a 3.5-year-old and a 1-year-old, and I borrowed a thermal camera from the lab and decided to try and photograph my son to see if his back lit up, which it did look
It's
quite
between the shoulder
convincing.
blades, isn't it?
Yeah, so,
you have a big patch of it.
and we have mainly in humans, it's found more actually in the neck, and there may be some between the shoulder blades as well in infant humans. But yeah, so it was
So that's your
not
own
ethical.
inbuilt central heating system.
Into heat, yeah.
Matt?
I think my vote for most efficient system, kind of just piggybacking on what you said about biological systems, I think my vote for most efficient system might be a person on a bike. So you can transport 100 kilograms or more, hundreds and hundreds of miles on, relatively small input of energy.
So the wheel was an amazing thing.
It was.
Yeah, I think it's 5,000 years old, the wheel. So, we made probably one of our most important inventions in efficiency terms, you're arguing, a long time ago.
Yeah, that's right.
Well, thank you, Matt. I'm going to quickly sneak this one in for you, Sam, because Jim wants to know, why do women live longer than men on average? What's the mechanism behind that?
Okay, so that's a good question and quite a big question, because it's not just men and women, it's loads and loads of different animals throughout the animal kingdom down to insects. And so,
where you see a sex bias,
where you'll see a bias
female biased
in their longevity. Mostly it's biased towards females living longer, but there are some reversals and some where you don't have a bias. And what it comes down to largely is that in many species, males and females have very different requirements in terms of how much effort they put into producing children, essentially. So in many species, males will mate and then disappear off, whereas females will then have to produce the baby. So for men, the optimum is to essentially mate with as many females as possible, whereas for females, you want to be picky about your mate because you can invest a lot into that baby.
But if I could challenge that, because that's all very well, you're reproducing when you're young, but we're talking about people living a long time, and many species don't reproduce when they become old, including humans. So there must be something else which is driving the persistence of these older females in the population then.
So this seems to be quite a majorly human thing, that this sort of aging aspect to it, in terms of the menopause in particular, being so far removed from when we die. In a lot of species, it will be a lot closer. So why that's occurred is a very good question. And interestingly, one of the sort of hypotheses has actually been to do with the way human structures have built up, favouring, bizarrely enough, the idea of men becoming more attractive and more suitable as mates as they age, which has actually put a drive on male longevity.
Is that just wishful thinking? Or
it's called the patriarchy hypothesis, which then has dragged up the whole lifespan of both men and women, but then have a bizarre question of why aren't the men longer lived than the women? And so then the sort of flip side comes that male sort of secondary sexual characteristics and tendencies towards violence and risk-seeking behaviour to try and compete for these mates drive down their age. So the two things combine.
Because if you look at conceptuses, the number of babies being conceived, there's a slight bias towards more male babies are conceived, but then about the equivalent numbers of male and female babies are born, and then after that, pretty much there's an excess of females forever.
If you say so.
Yeah, I mean,
I'm not aware of that one.
But it's interesting sort of, that's actually the figures that we see. And so it seems like there's this sort of bias initially in favour of males in order perhaps to counteract the very thing you say, which is that males are more risk prone. So who knows anyway.
Possibly, yeah.
Helen, I mean, a lot of this must chime with your research on cars and driving and that kind of thing.
It does, and I know from risk-taking behaviour studies, there's obviously there's a big difference between risk-taking behaviour in young men and young women, but this risk really decreases in older drivers as we get older. So it can't fully account for the difference in life expectancy between men and women, although it does input into it. But as a psychologist, I think something really interesting to me is the protective factors of socialisation as we get older. So socialising with people protects you against all sorts of things like Alzheimer's Alzheimer's and dementias, but also of death itself. It adds years to your life. So we know that older women are more likely to have a greater social network and a richer social network than older males. And I think this might feed into this longer life expectancy.
Because on the subject of the driving side of things, it sort of overlaps with this question, which we've got for you from Liz.
Are some demographics simply better at driving than others?
I suspect that probably male, female, the insurance companies know this very well, don't they?
I always find this very funny. I mean, as a driving researcher, by a better driver, we mean a safer driver. And unequivocally, women are far better drivers than males. Males account for 75% of road deaths, but they're responsible for upwards of 90% of fatal road accidents.
And
so
sorry to interrupt,
yes.
But I just would like to clarify. If you stratify that by age, does that hold right the way across the age spectrum, or is 90% of that people under 21?
It's a good question. There's going to be different things feeding in here. So at a younger age, absolutely, we know that risk-taking behaviour is really prevalent among young male drivers compared to younger female drivers, and differences do get less as we get older. But then some more differences start to kick in around ageing, which is something else I'm interested in. Older drivers are prone to errors when they're driving more than younger drivers, and gender differences hold for older people. Older men are worse drivers than older women. But it does bring up an interesting question about how old is too old to drive. So there are things that are quite obvious to us. So older drivers, their vision is worse than younger drivers. As we get older, we lose flexibility in our lenses. So our ability to focus on distances gets worse, our peripheral vision gets worse. But really importantly for night driving, the ability of our pupils to enlarge and take in light gets worse as we get older, and it becomes quite fixed. So our night vision really suffers as we become old. But interestingly as well, we have a loss of white matter as we get old. And white matter is part of the brain where the nerve axons respond much quicker than in other parts of the brain. And we have a lot of this activity happening in white matter when we're younger. So as we age, we have a loss of white matter. And these differences can't really be corrected for. These slower responses, we can't correct for them just with glasses and hearing aids and better vision. Our brain actually responds more slowly as we get older.
Indeed, the white matter is the connections between different bits of the brain, isn't it? So if you lose those connections, I suppose the bandwidth, the processing throughput rate the brain can handle is going to diminish a bit as we get older.
Absolutely right. So we have myelin sheaths on these nerve axons transmitting information that makes information go really fast. And if we lose that, it's really irreparable. We can't really compensate for that loss. There was a very interesting story in the news recently where police in 3 areas of the UK are going to start mandatory eyesight testing for every motorist that they stop. And this is related to something called Cassie's Law, where an 87-year-old male driver was pulled over and tested by police for his eyesight, and he didn't pass that eyesight test, but yet was allowed to continue driving. We know that if we bring in these mandatory eyesight tests for elderly people, it can have a real impact. And we ask how old is too old to drive. At the moment, if once you hit 70 in the UK, you have to renew your licence every 3 years. So that might be a bit protective, but really it's going to be on self-report about whether your vision is still appropriate for driving. So, road safety researchers would like to propose maybe that once you hit 70, there are mandatory eye tests involved. And not just eye tests, but like I talked about this loss of white matter and this slowing of responses, perhaps even mandatory driving tests every year or more frequently once you hit 70 years of age.
You never know, though. By the time us lot hit 70 years of age, perhaps we won't be driving anyway. So this problem might sort of get solved by technology. We may be dumping ourselves off in our driverless car, and it won't matter if we can even not see at all. We'll get where we need to go quite safely.
I hope so, because I think driverless cars are absolutely the future, although it would do me out of a bit of a job. But I think there is something to balance here. When we say that as a demographic, older drivers are more dangerous than younger drivers, we have to look at relative versus absolute risks. So relatively, older drivers are more error prone than younger drivers, but at an absolute level, they make far fewer journeys. And when they do make journeys, they travel far fewer miles, far less distance. So on an absolute scale, really, if we were to just to target road safety, we'd probably still just be aiming at younger males and getting them all off the road now.
Thanks, you've just offended 99%. No, I'm just kidding. Probably about 95% of our listenership. Thank you very much for that, Helen. On that note, we must leave it because we have run out of time. But I have to say a very big thank you to our panel this week, who are Matt Bothwell, Helen Keyes, Peter Wuthers and Sam Virtue. Katie Hayler and George Mills put the programme together. Do join us at the same time next week when we'll find out whether the North Pole is about to become the South Pole. We'll be exploring the Earth's magnetic flip. Do join us to find out what the consequences might be. The Naked Scientist comes to you from Cambridge University and it's supported by the EPSRC and Rolls-Royce. I'm Chris Smith and thank you very much for listening. Goodbye.